In section 3.3, we are going to talk about sampling distributions and the central limit theorem. And the idea of a sampling distribution is a very abstract notion. So I think it's a tough thing to understand. And what I'm going to try to do in this video is very briefly give you a sense for what a sampling distribution is and how we're going to use it. Remember, the main idea of this course is that we want to make claims about populations from samples. And in particular, if we want to figure out what a population mean is, the way we're going to do that is estimate it from a sample. So we want to know the population mean. We can't actually access the whole population and measure the variable on the whole population. So instead we do that for a sample and we calculate the sample mean. And this whole exercise is relatively useless if we don't know how good of an estimate our sample mean is for the population mean. And this is where the notion of a sampling distribution comes in. So right here, I have a histogram for a population. So this is something that I just created on my own in RStudio. And we're saying this is our whole population, but let's suppose that we didn't actually know that, right? In general, you wouldn't know the values of a data set over a whole population. But this is a histogram for the entire population data set. And if I were trying to estimate the mean using sampling, what I know is that different samples will give me different values of the sample mean. And the question is, how will those values vary? So now we're saying, look, what we're thinking of this situation is we're thinking of the samples as the individuals in the population. Every possible sample from the population, in this example, I think I'm doing samples of size 100. Every sample of size 100 will give you its own sample mean. That's a data set. What does that data set look like? And using software, I went ahead and did that. I didn't get every possible sample, but I got a lot of them. And it turned out that the distribution of sample means looked like this. And I'll flip back and forth a few times, but I want to highlight a few points. The first point is that my population histogram was left skewed. This histogram looks relatively symmetric. So the histogram of sample means was in some sense a nicer looking histogram than the histogram of population values. The second thing I'll point out is to zero in on the x-axis here. Notice that these values are all relatively closely packed together. They're separated by 1 overall, whereas the population data set was kind of widely spread out. So when we take samples, our sample means are closer together than the values of the original population were. I think this is a relatively intuitive idea, that sample means shouldn't vary as much as the population values did. And so what I want to do to kind of put this into even more perspective is put these things on the same axis. So here, what I've done is in, I guess, pink or red is the population histogram. And in blue or purple, depending on how this comes out in the video, is the sampling distribution, the distribution of sample means. And so you can really see that they're way closer clustered together. If you're wondering about why it goes so much higher, the idea is that when we scale our histograms, we should scale them to have the same area under them. In this case, I've scaled them both to have an area of 1 under them, representing all possible values. So I've scaled them appropriately, and so you can see that this is how it behaves. So this is good. This is reinforcing our notion that that when we estimate the population mean using the sample mean, we should get reasonably good estimates. That is, our sampling distribution, the distribution of all possible sample means, is narrow. It's not too spread out. So going back to the histogram of sample means, it's not just that it looks roughly symmetric. As you look at this, you might realize, this seems like it could be a normal curve. And we never want to claim that a histogram is exactly normal, because any histogram, it's an approximation. We're putting stuff together into bins. But what I'm going to do is I'm going to draw a normal curve on top of this, because I know what normal curve it should be. And it turns out this looks really close to a normal curve. That is, we can see that this curve I've drawn over it crosses through each bin of the histogram, each block corresponding to a bin, right near the middle. So this looks really close to normal. And that's what the central limit theorem is going to tell us. It's going to tell us that under certain circumstances, if either the sample is large, above 100 is the boundary we'll use, although other people use different boundaries, or if your original distribution was normal, then your sampling distribution will be normal or approximately normal. And what this allows us to do is it not only says it's normal, but it tells us that the mean is the same as the original population mean. So our sample mean is an unbiased estimator. It on average is right. And it also tells us how spread out it is based on the population standard deviation. So the central limit theorem is going to tell us exactly how close we should expect our sample means to be to the population mean. And this is really nice because it turns out that it didn't matter that our data set was left skewed, which is great because data sets can have any sort of shapes, and population data sets could be bimodal, they could be strongly skewed, they could be normally distributed. There's so many different shapes they could have. The central limit theorem is telling us, look, if your samples are big enough, then your sampling distribution will look like a normal distribution. And that's going to allow us to do a lot of calculations in this course. So that's the whole idea of 3.3 and the idea of sampling distributions. And as I said, it's a pretty high level notion, this idea of a sampling distribution. So put some thought into it and don't get frustrated if you find yourself confusing different ideas, the idea of a sample, the idea of a sampling distribution. It's something we'll work with throughout the course. And as it turns out, I think we'll hit a point where you're not really thinking about the central limit theorem and sampling distributions all the time, because the nice thing about the central limit theorem is it will ultimately boil down to a couple really nice formulas. And so when we're doing calculations with it, it'll be in the back of our minds. It's not something we're constantly thinking about. So that's the idea of this section. Hopefully that video helped you to get a sense for what we're trying to do.